So it's already right. It's already 6 a.m. So for today, we continue our lecture, International Series Lectures on Bioprocess Engineering 2024. So especially it's about the bioreactor engineering. So I would like to introduce myself again. Yesterday, I already gave a talk about the introductions of bioreactor engineering, specifically batch fermentations and introductions of bioprocess. Then for today, I will not be a speaker or the lecturers for this international series lecture, but I'm just a moderator. So today we will have my friend here. Thank you for coming here, Mateo, and thank you for the times. He's my late mate. We work at the same research group, and he worked a lot about chemostat because he will talk about chemostat, like the basics of the chemostat. Before we start our lecture, probably I would like to introduce another speaker for our lecture series here. She's my limit as well. She's a PhD student, PhD candidates in our research group. And especially for this lecture series, we will have another lecture. So yesterday, probably I just say that just 5 lectures until 5 weeks, but we will have an additional lectures. And I think this is so important. It's about photobioreactor, especially for algae fermentation. And her name is Anggana. Is Anggana here or not? Not yet. I don't think Anggana is here. So yeah, we will have another lecture. It's about the photobioreactor. And then this is last week. We already talked about bioprocess engineering scope and fermentation, and then anaerobic fermentation, especially biogas productions and the other metabolites produced from anaerobic fermentation. And then batch fermentation bioreactor, like the basic concept of the batch fermentation bioreactor. Then a batch bioreactor components and how to set it up, and then the parameter performance evaluations. And if you still want to, learn again the lecture that I already shared with you, you can go to our YouTube channel. We have YouTube channel here, Proditin. Just go there, and then it's already uploaded there. So you can rewatch our last week lecture. And then
Uri,
this is a yeah.
so sorry, we are not
Mhm.
seeing you moving the slides.
Oh, I'm so sorry.
We can see just the PowerPoint.
Okay. Okay. Hold on. What's going on here? Okay, can you see my PowerPoint here or
Yeah.
not?
Yeah, now we can, yeah.
Okay, I'm so sorry. Okay. So yeah, you can rewatch the lecture, last week lectures, and you just go to our YouTube channels, Proditin. The lecture one about an introductions to bioreactor engineering is already uploaded there, and you just go there. Then this is what we already learned. Like this is the conclusion of the last week lecture. And for batch fermentation, you can see this kind of the graph. It is a cell curve and adaptation phase, and then exponential phase, stationary phase, and a dead phase. And then what we want to have here, because batch fermentation is not a steady state steady state. So that's why we want to have like the steady state conditions, and we need to make the process to be continuous. So that's why, like, for example, we want to maintain the mu max here. The mu max can be achieved when it reach the exponential phase, and then we want to maintain the mu max to get the optimum production as well. So we have to change it to continuous flow here. Then for the continuous flow, our chemostat. We know chemostat. Mateo will explain to us about the chemostat. Then, yeah, this is Mateo. So there are several, this is the outlines for today, the definitions, important and key parameters of a chemostat, and then mathematical modeling, and examples of calculations for chemostat, and then application of chemostat. And this is the background of our speaker today, Mateo. So he graduated in Colombia, right? I'm not really sure how to pronounce your university here. So is it ICHES?
It
How
says
to
C.
pronounce? ICESI. Okay, ICESI University. All right, ICESI University in Colombia, and he actually just held bachelor degree, and then he just jumped directly to PhD. Probably I wanna have like little chit chat here, like small talk. So how I mean, not most of, like some of the PhD students in United States especially, they actually just skip the master program, the master degree, and then they actually just directly jump from a bachelor to PhD, and including Mateo. So do you want to share your experience, like how to get this position directly from bachelor to PhD? Because like in my country, in our country, it's rare. Even though we already have the program, but the scholarship as well, but it's rare. But in the United States, it's so common here. So Mateo, by the way, he's still 24 years old, and he started his PhD when he was 23 years old. Probably you want to share your experience.
Well, maybe yes, the bachelor is different from most of the countries because we study for 5 years.
Mm,
So it's 10 semesters, and we reach pretty close to 300 European credits.
mm-hmm,
That is in Europe, like 240 are for bachelor, and then 60 credits are for masters. So in terms of the credits,
mm-hmm.
our credit system is pretty close than a bachelor and a master's.
Oh,
But
okay.
it's difficult to get, for example, a PhD in Europe because they always will ask you for the master's degree and you
Yeah.
don't have the diploma.
Mm,
So sometimes it's difficult to get a position of a PhD student in Europe, but in the United States, that is not usually a problem. You can jump from bachelor to
mm,
PhD
yeah.
if you just reach out to your to a PI or supervisor, and if he
Okay.
likes what you have done and everything, then you will get the entry.
Oh, okay. So that's possible actually if you just directly want to be academia, and that's gonna be, yeah, better probably just from from bachelor to PhD, I think. So but if you want to work in industry, yeah, probably you can do master. But if you want to be academia, and then you just jump from bachelor to PhD, I think.
Okay.
All right. So another slide here. Oh, it's done. So I think, Matthew, you can start the presentations. Yes,
So let me share.
sure. All right. Yeah, I can see your presentations here.
You can see?
Yes, yes.
Okay, so hello everyone. I will talk about continuous flow bioreactors. Already Budi introduced me, but I'm Mateo Gallardo Atehortua, bachelor, and right now I'm doing a PhD in engineering science, focusing on bioengineering. So in these lectures, I will talk about my background first and the research that I'm conducting right now. And why? Because I'm working, as Budi said, in with the help of chemostats, and I think chemostats are a very powerful like tool for the research that I'm conducting, and I will talk about more about. what I'm doing in the next slide. I will also let you know the objectives. Uh, what are my goals with these lectures? What I would like to like see it in every one of you. And in the third one, we will go more in the matter about continuous flow bioreactors, talking about basic configurations, assumptions, some calculations. I will not go so much in detail about any calculation, but I would like to show like the most important formulas that we use and also the importance of this type of bioreactors. And finally, I will talk about the applications. And I brought some diagrams about glutamic acid and bioethanol production, where we can see a continuous flow bioreactors. So nobody talk about me a little bit, but I'm about chemical engineering from ICESI University, based in Cali, Colombia. My thesis was about catalytic glycolipid formation from peach palm fruit shells using reaction systems with natural deputecting solvents. Um, in this case, for this thesis, something interesting was that the solvent was not water, and water was an inhibitor of the reaction. So usually in the systems, in the biocatalytic systems, we have water as solvent. But this is an example that sometimes the things are not that ideal as we might think. So we need to like generate new ideas and come up with different solutions to the problems. Right now, I'm a bioengineering student, PhD student at Washington State University. And I decided to focus my research and my professional career towards environmental biotechnology because I truly believe that environmental biotechnology is the one that could have one of the greatest impacts in the world. Right now, we're seeing a lot of um, environmental problems, global warming, hurricanes, and um, worry about that. And I've been worried about that since many years ago. So I decided to move my career towards this field. Well, now about my research. So about my research, I'm working mainly in adaptive laboratory evolution. So this concept is um, could be kind of like new, but it's all about the theory of evolution, the Darwin theory of evolution. So uh, I would like to ask maybe Woody, are you there?
Yes, I'm here. Sorry.
So just to make more like questions and
Mm-hmm.
uh, about the Darwin theory of evolution, what does that theory say?
The evolution.
Mm-hmm.
The evolutions can create the new organisms based on the time over the times.
The
So because
times.
of that, there are several effects, for example, like the stress conditions or whatever, there is the conditions over that time. The time is so long, like very, very long, and then it can change, the organism from one thing to another things. Is it
Is
correct?
this? Yeah, 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 it's true. Because during the time, a microorganism that is exposed to a perturbation might die, but with a lot of time, some mutations will create a better strain, a better microorganism, so we can evolve. Just like we evolve, the microorganisms can also do it. So in this case, the idea of the adaptive laboratory evolution is recreate the evolution, but in a laboratory scale. So this is a very powerful molecular biology technique because aside from the genetic engineering, sometimes we don't know the whole genome of a microbe. For example, if we think about E. coli or Saccharomyces cerevisiae, those are like microbes that we know very well in detail the genome. So we can make we can think about if we want to produce this, then this gene will be the target and this other one. But if we are dealing with microbes that we don't know the genome, some microbes that we just found in a reactor like the one that I'm working on and that is new, then it would be difficult to do genetic engineering. So that's why I'm doing adaptive laboratory evolution of this microbe to increase the resistance to some different perturbations. So the idea with this microbe is that if we can increase its robustness, it means the strength to withstand different perturbations, then it will be a better industrial microbe. So we can upgrade biogas and produce renewable natural gas. So this is very powerful because from CO2 that is already in the, let's call the atmosphere, for example, from this CO2, we can produce methane. So it creates like a circular economy loop. So it's pretty good to decrease the emissions that we're doing every day of methane and CO2. So how this work? Okay, so it can work in liquid media, for example, cereal dilutions in liquid media. It can be also in plates, for example. So the idea is that every time you grow a microbe under a certain perturbation, you will reach some mutations. Then the result could be that they die or they survive. But if we keep pushing the microbe and you create more and more generations, someday the microbe will get the right mutation in the exact moment and it will be able to withstand the perturbation. This is also carried out in chemostats. So why chemostat is that important for this? Because with chemostat, we can select a point in the growth of the microbe. So if we can select a point in the growth, we can say, okay, I would like to start my perturbations when the microbe is in the middle of the exponential phase, when it's reproducing a lot of times and creating more and more microbes. So if we create more and more microbes, we will have more and more opportunities to get the right mutation. That's why the chemostat is so important. And this is a graph of a chemostat when we can see all the factors constant over time. Of course, at the beginning, it will not be like that, and we will talk about that. So as I said, it can increase the fitness. Fitness is also a way to call the microbes that can withstand the perturbations and that are very strong. And there are different types of mutations, no? So the objectives with the lecture is understand the fundamental principles of chemostats, analyze design and operating parameters, for you to identify industrial applications and reflect on sustainability and future applications. So continuous flow bioreactors. The concept is to have a reactor with concentration of product, cell, substrate, and chemical properties constant over time. The assumption that is perfectly mixed. That is the most important assumption. So how this work? We have our vessel and we have fresh media coming in to the reactor, and there is also effluent that is coming out of the reactor. So in that way, we can maintain our volume And we will need pumps for injecting media and sometimes for extracting the exhausted broth. And also in industrial scales, it's very important to have a lot of sensors so we can measure every time the concentrations and some different parameters. So for the ideal chemostat, it's perfectly mixed. So the concentration of the chemicals inside of the reactor is the same as the outlet, but not the inlet. So this is very important when doing the mass balance. So for the mass balance, we have the rate of accumulation equal to rate of input minus the output plus the generation or consumption. It depends. But in this case, it's of cells. So we are generating cells. So we have the inlet, that is the flow, times the biomass that is coming from this inlet. Usually, we inject fresh media in the vessel. So usually this x0 is equal to 0. So we neglect sometimes this. Minus what is going out of the reactor. We're always getting like biomass in the outline. So this will not be 0. And we have the formation of biomass and also the biomass that are dying inside of the reactor. And this will be equal to the rate of accumulation. It's always important to multiply times the volume because dx is concentration and we don't do balance of concentration, we do mass balance. So it's always important to keep that volume into account in the balances. So from this, there is like the magic of the chemostats, and we will know why. When we divide this expression by the volume, we will get flow over volume, and that is equal to a concept called dilution rate. So the dilution rate is very important because it's the reciprocal of the residence time. So when we have this accumulation now equals to this expression, we know that x is 0, and usually the specific growth rate is bigger than the death rate. So we will have dx, and we have a steady state. This is important. So steady state means that there is no change in the biomass. So this differential is 0. So we get 0 equal to dx 0, but this is 0. And we have mu g times x minus dx. And if we make the calculation, then we get that mu, that is the specific growth rate, is equal to the dilution rate. So in this case, this is a very powerful concept because it means that we can manipulate the growth rate by changing the dilution rate. So the dilution rate is the flow over the volume. The volume will be kept constant, but we can play with the flow as we wish. So we can increase the growth rate or decrease the growth rate depending on what we want. Also, this is powerful because we can select in this way in which point of the growth rate we would like to maintain ourselves in the chemostat. But this is like, is this something like with no limit? And well, in nature, there is limit for everything. So this is not an exception. Because if we keep increasing the dilution rate, we will reach one point where we can create something called washout. And it makes a lot of sense because from the last lecture that Puri was giving you, the cells grow, but there is a limit. There is a specific growth rate that is a maximum for the microbes. That even if you increase more the substrate concentration, you will get no more specific growth rate. And this is called the Mumax. So if we keep playing with the dilution rate, trying to improve our specific growth rate, and we are not careful with this concept, then we will be diluting our cells. And we dilute the cells, they are not reproducing at the same velocity than the velocity that we are extracting them from the media. So at the end, we will have media with no cells, and this is called washout. So some ways to solve this problem is by retaining cells in the fermentation liquid or by cell recycle systems. So how is this? We have in the outside, we connect the outside with a separation process so we can get the cells from that process and we can introduce them again in the vessel, in the bioreactor. So we will be making sure that we have enough biomass in that loop for preventing the washout every time. For the substrate mass balance, we have the same basic concept, accumulation equal to the input minus output plus generation. But in this time, the substrate is consumed. So we have negative values and it's consumed not because we are producing biomass, but also because we are producing product. So we have also this formula. And we have a steady state assumption, and our KD is not as big as our specific growth rate. So at the end, we will reach formulas like this one, where we can use the yield to calculate the biomass. So at the end, we will be able to get this linear equation. So this is important because from experimental data, we can calculate the yield of substrate in biomass and also the maintenance coefficient like this. So we can have our intercept and our slope to calculate these two parameters. So now we have these two equations. We will get more in the way. Let's see. The mass balance of product, we do the same thing with the substrate, accumulation, rate of input, we are not introducing the product, and output, that is the flow times the concentration of product, plus the rate of generation, that is RP times the volume. And RP is equal to the specific production times the biomass. It's a specific because it's divided by the biomass that is producing this metabolite. And at steady state, we have this differential equals to 0, and we have that Dp is equals to Qp times X. And from the mass balance, now we can introduce this new formula, and we can know that this that X is equal to the yield of substrate in biomass times the difference in the substrates that is in minus the one that is actual in the reactor over the dilution rate over this expression. Now we have this another formula, and we keep this one to determine the substrate. Now something important is the productivity. We will be asked about this when we are conducting our experiments on industrial processes. They will always ask, how much are you producing? In how much time? So we know that the productivity is equal to the dilution rate times the concentration of product, and also the dilution rate times the concentration of biomass. This is for product and biomass. But if we are asked about what is the maximum that you can get, then we will have to make a derivate. We will have to derivate dp over dd. And if that is equal to 0, it means that we are in a maximum. So from these formulas, when we differentiate, we get these expressions for our optimum values of dilution rate, concentration of biomass, and we can get the productivity, optimum productivity. So as always, the substrate that is inside of that is in the inlet is much bigger than the Ks. Then we have that the dilution rate optimum is equal to the mu max. But again, reaching this is very difficult because it's difficult to keep constant this flow rate and the working volume, but also because we're getting close to the washout point. So the dilution rate will not be the optimum. As a conclusion for these mathematical expressions and calculations, we have some formulas that can help us to determine the amount of substrate when the maintenance and the death rate is neglected, when it's considered also. We will be able to calculate the amount of product using this formula, and the amount of biomass when the death is neglected and when it's considered, and also to consider when it's considered the death rate and the product formation at the same time. The importance of these reactors is huge, and it is due to it makes us able to produce in a continuous way the metabolite that we desire. And why this is important? Because it decreases the downtime for the batch. For example, when we compare with the batch, we always have a downtime that is the period of time of preparation of the bioreactor, and also for the preparation before the fermentation. And when it finished, we also need to clean, and we need to make it aseptic again. So this is the downtime. And in a continuous bioreactor, we don't have this disadvantage because we can run for like a lot of time, months. But usually, it's also important to say, um, industrially and experimentally, it takes time to reach a steady state. So you can take probably 1 month to reach the steady state of a continuous bioreactor. And then you will not stop. So some depending on the company, there are periods of time that they select to stop the production, clean the reactors, check and do maintenance, and then run again. But these periods of time are like years, probably every 1 or 2 years. And we will not want to stop the process because this will like introduce this problem of opening again, cleaning, and reaching the steady state. So this will keep going all the time. Also, an advantage is the precise control of the growth parameters, because we have everything constant, so we can select based on what we want. For example, there are types of chemostats that work on, they want a pH constant. So it can be a pH stat. Or if you would like your key parameter, the biomass constant, then you will have a turbidostat. Or if you want, for example, to produce penicillin, then you know that penicillin is a secondary metabolite. So as it is a secondary metabolite, it is not produced in the exponential phase, but in the stationary phase. So if you have a batch, you will produce just once. But if you have a chemostat, you can select that OD when the microbe is at the stationary phase, and you can keep it like that. So you will produce penicillin at the higher rate all the time. So you will get more penicillin. Also, control of limited nutrients. So continuing with the example of penicillin, they usually have a nitrogen limiting environment. So we start from low nitrogen concentrations, and then it will make to the microbe to reach the stationary phase faster, so we can produce the penicillin. So we can also play with these limited nutrients. So more applications. I brought this PNID for the glutamic acid production. We have a upstream process, especially a continuous sterilization. And then it is put into the fermenter, where we have cells usually of C-glutamicum that can produce this amino acid. And we have different controls for this chemostat, as I was saying previously. And then we get the downstream line to a decanter. Then we use sulfates to help the filtration process. We have a treatment with carbon, and we have different downstream processes. Until here, we reach the point where we can have a technical grade, but if we have an edible grade, then we will need a third bleach, fourth bleach, and then we have edible glutamic acid. This is a very good example, because glutamic acid is produced in lots of tons per year. More than 2.8 million of tons per year. And it is because it's highly used in the food industry. So when we have products that we need to produce a lot, then we might think on using a chemostat or a continuous flow reactor, because we will have the production constant at the highest point. Also, another example is, well, this is not biodiesel, but this is bioethanol that we can use after this to produce biodiesel. And in this process, we have the sugar cane. We have these sulfitations to clean the juice, and then a liming process, a heating, clarifications. We then evaporate to concentrate the sugars inside. And then we have crystallization processes. But from this crystallization, we centrifuge, and then we have some liquids, so we can use for the fermentation. Sometimes also syrups are used from these stages of evaporation, depending on the demand of bioethanol. And this is an example of cell recovery, for example. From this fermenter, we have an outline and an outlet line of yeast recovery. So usually we have another centrifugation, so we can collect again the cells. It can be Saccharomyces cerevisiae or Simomonas mobilis, for example. And we can keep these cells and we can put it again in the fermenter. So again, there is a limit for this. And every time we do this, this is called generations. So we have a limit of generations. And why? Because cells are like, they are alive. So we need to treat them nicely also. And they will reduce their the vitality and viability. And it will reach some point where the cells are not like good for the use. And we will have to generate again a new inoculum. After the fermentation, we produce ethanol, and it is concentrated in distillation processes and then purified in dehydration processes. Usually in these stages, we use zeolites to trap any small particles and purify the ethanol to get more than 97% ethanol even. Also, why we use continuous process here? So this is the criteria for this is that we have a limiting point for the ethanol production, because when ethanol is produced for more than to reach more than 15 grams per liter to 20 grams per liter, no, 15% to 20%, sorry, of the ethanol inside of this liquid, then we will inhibit the growth of the microbes. And if we kill the microbes, then they will not produce ethanol. So we can, with a continuous system, we can select a point where we can say, okay, let's reach just 14 grams, 14% of the ethanol. Then we can play with the formulas that I just showed to you and select a flow, dilution rate that we can get that 14% of ethanol that is close to 15, but is a little bit less because we want to produce as much as we can, but we don't want to kill our microbes. So I think this is the presentation. Let me see.
We actually still have like one more hour.
Okay, yeah,
Oh, yeah,
for
it's okay. Yeah, that's so interesting presentations. Yeah, thank you for the presentations, Mateo. And we already learned a lot of things about chemostat and the applications of the chemostat as well. I understand that chemostat is not that easy, not as easy as the batch fermentation bioreactor, especially for the batch fermentations bioreactor. Yeah, so I actually have following questions for you. Like, you already mentioned about the advantages of chemostat. Now, what is the challenge of the chemostat itself?
well, challenges are in the theory. I mean, when we're learning about chemostat, is that we
Yeah.
have a lot of chances of contamination, for example,
Mm-hmm.
because it is not like the batch when you start the process, you just close and
Mm-hmm.
then you finish and then you open. In
Mm-hmm.
this case, it's like in continuous inlet and outlet of chemicals. So if we have one mistake, it will
Mm-hmm.
get contaminated.
Okay.
That is one of the most difficult ones. But in my experience, setting up these kind of reactors, the
Yeah.
setup of these
Yeah.
reactors is very difficult. I
Okay.
spent like 3 months trying to set up one chemostat, and I'm still trying to get the steady state. So
So, so what's the challenge when you set it up the chemostat itself? Like, um, can you describe it? Like, what's the problem there?
is select the vessel or the reactor. So sometimes people can use different brands, for example, Applicon or bioreactors,
Mm,
but sometimes the bioreactor itself is not made for you. So, for example, in my case, I need an anaerobic chemostat, and
mm.
it makes the things way more difficult because I cannot allow to have leaks. And that is the main problem of
That's
this.
especially for the gas fermentations, right?
For
Yeah.
these gas fermentations. So we need to keep a certain pressure of gas substrate in the reactor. And if we have any small leak, one small hole, you will lose the substrate and then you will not be able to do anything. So for me, finding the fittings, finding tubes, the right pumps, selecting the flow rates, and then thinking about the problems. So doing troubleshooting. So if this
Mm,
is not doing well, what is happening here? So the gases have different densities. So we need a recirculation line because we need to mix the gases.
mm,
So sometimes perfectly mixed is not always just liquid mix. No, we need to mix the gases also.
mm.
So,
Yeah.
but I think that is what construct the PhD.
Yes, I really understand about it because I also work on gas fermentations, and we actually have a lot of problems for the gas fermentation, especially for the leakage. So yeah, so what's the difference between the chemostats in the lab scale and an industry? Probably you already have experience in the industrial scale when you work in industry.
First, I will say that sterilization, for example,
Yes,
in the
sterilization.
lab scale, you can just autoclave the bottle, autoclave your media, and autoclave your materials, but you cannot autoclave a big reactor.
Yeah.
Uh, so, well, for that, we use different processes that are called CIP or SIP, SIP and
Mm,
SIP. The cleaning in place, we use usually soda, for example, sodium hydroxide,
mm,
no, or also acids like hydrochloric acid to clean every residue that we can have. And
mm,
then steaming in place, we use steam to sterilize the reactors. So it's not as, I will say that it's not good as an autoclave,
mhm,
but it works. Another thing is that, well, the volume, the amounts of volume that we can use also increase the need for more robust sensors. And we need sensors that can measure the level because of the foaming, for example. You can produce foam, and then
mm,
you will need anti-foam agents. Um, if you need to measure the oxygen, if it's an aerobic process, and also the CO2, you also need sensors. And yeah, I would say that mostly those different.
yeah. Yeah. So one of the biggest problems in chemostat actually it's the occurrence of the washout. We already know if like you give like a lot of like higher dilution rate, for example, and probably the cell also will wash out. So so do you what is the strategies to avoid it, the washout itself? You already mentioned like the cell recycles and probably what anything else, or you can explain it again probably.
But to explain this one, and for cell recycle, you can keep biomass in your hand. Like, let's say from the outlet line, you keep you centrifugate, then you get cells ready for injecting again. So if
Mm,
you see that you're getting a washout point, then with this recycle line, you can introduce more cells so it can increase again the
mhm,
amount of cells that you have, and then uh, be like a little bit far from this washout point. So that's how the recirculation works. But you can always think about different reactors. For example, you can immobilize your cells.
Yeah.
So, and
Mm,
in that way, it will be easier to do the separation process. You can use a simple filtration, get
mhm.
the immobilized cells, and then put it again in the reactor. Or
Yeah.
you can also have the immobilized cells always in the reactor,
Okay.
for
Kind of
example.
like a gas bioreactor, right? Like you,
Mhm.
yeah, you put it the cells inside of the bioreactor instead of you just flow out the cells and then go to the filtrations there. Yeah.
In that way, they will not go out. They will always stay there.
Yeah,
You
just
just
stay
need
there.
to keep them alive.
Mm-hmm. All right, that's good. Hmm. So now Q&A, questions and answers.
Mm.
Probably anyone here want to ask the questions here? Oh, Maura. So we will have Maura, Azara, and then Igade Wismaya. Probably Maura, can you are you here? Or you want to?
Yes, I'm here, sir.
Yeah,
First
yeah,
of all, sorry, I cannot on my camera because the
sure.
condition here is not very conducive.
Yeah.
And I'm going to introduce myself first. My name is Maura, and I
Mm-hmm.
want to ask for Chemostates, how do different design and operating choices affects how well a continuous bioprocess works and stays sustainable? Called Mr. Mateo gave some examples of industry that use these choices to improve their process, especially on agricultural industry.
All right. So do you want to answer it, Mateo? Do you get it? Is Mateo here or
Okay.
not? Oh,
Yes, I'm here.
okay. So do you get the point of the questions or you need to?
Maybe can you maybe explain that one? Hmm?
Yeah, Moda, can you can you repeat it again? So I'm so sorry. I also
Okay,
don't
okay.
get the point. Sorry.
So I have the question.
Yeah.
First of all, for chemostates, how do
Mm-hmm.
different design and operating choices affects how well a continuous bioprocess works and stays sustainable? That's the first question.
Okay. Oh,
And
do
the
you mean
second,
sorry, the difference, like there are many types of the, the chemostats, and then what's the difference? Do you mean like is there any the other things, the other types of the chemostat
yes, I
that you
want to ask about that, like different designs and operating choices. And
oh,
the
design
second
operating.
question, I want to ask about the examples of industry that use these choices to improve their process, especially on agricultural industry.
Okay.
In
To
this
improve
case,
the
I don't have an
process.
agricultural background, so maybe would
So for the first questions,
yes.
probably.
So for the operating uh, yeah, ways or operational parameters with these chemostats, we can decide towards what we want. So for example, in my case, with my research, I will always go for turbidostats, for example, because what I care more about is that I can have my cells at the same specific growth rate. So in that way, I will select a turbidostat because I want the same amount of cells over the time. And I will measure always the OD in time of this chemostat that I'm using. But sometimes, let's say, for example, the ethanol production, then you will have to be more careful about the ethanol concentration. Then you will have to measure the ethanol over time and be very careful with um, getting the same amount of ethanol all the time. Otherwise, your cells will die and you will not produce more ethanol. So it's always depending on the design process. When we are designing processes, we always start from the product. What is my product? Okay, my product is ethanol, or my product is that my cells can get mutations, or my product is penicillin, or my product is that I want to destroy a polymer or produce bioplastics sometimes. So based on what we want, then we select, of course, the downstream process and then the fermentation. And we select our chemostat, and we can select the operational way we want, and also the different parameters that we have to take into account when working with these chemostats. I don't know if this answered the question. This,
Sorry.
Woody, this
Hello?
is,
Okay.
I hope that answered the question.
So how's the
But there
answer?
was another question, no?
Oh, so it's about the improvements of the process if you have like the agricultural waste or agricultural um, materials for so is it the questions or I'm so sorry. Who's the I forget the
Yes, I
name.
think Maura was the name.
Oh,
Yes,
Maura,
sir.
is it that questions like how to improve the process in chemostats if you have, for example, the agricultural waste or agricultural materials? That's your second question?
Oh, no. The second question is I want to know, is there any examples of industry that use
Oh,
these kind of choices to improve their process, especially on agricultural industry?
yes, of
Mm.
course. Yeah, yeah. Actually, Mateo already mentioned it about bioethanol productions. So bioethanol productions and then organic acid, because this is based on my experience too. I operated a acid anaerobic digestion. It's actually still semi-continuous. What's the difference between continuous and semi-continuous bioreactor? For the semi-continuous bioreactor, it's batch actually, but you just feed the reactor at a certain time. For example, you feed the reactor every day, and then stop it. And then another day you feed the reactor again, and then stop. And then another day you stop, feed the reactor, and then take the effluent. It's not continuous. So it is semi-continuous in the rest anaerobic digestion. Yeah. Um, so yeah, as the presentations today, like we can use we can produce ethanol, for example, from lignocellulosic materials, and then or the other types of the agricultural waste, lignocellulosic biomass. And then we also can produce, for example, organic acid, like VFA, volatile fatty acids from the waste especially. And then yeah, the waste or yeah, waste generated from agricultural activities too. So that's the example. We can basically for the chemostat, we actually we produce like the huge amounts of the products here. So it's not it's for the bulky products, but and then for the fine product, mostly they use the batch fermentations. For ethanol and organic acids, mostly they use the industry use the chemostat. So that's the answer. So
Okay, thank you so much, sir.
yeah, no problem. So we also have Igde Wismaya. Are you there?
Yeah, yes, I'm here, sir.
Yes.
Let me introduce myself first. My name is Igdeus Medarmadi Mukti from
Is it freezing?
Yeah.
Oh,
Mm.
okay.
Maybe the camera consumed a lot of
Yeah,
internet.
I, I don't think like okay.
sorry,
We can.
my connection
Uh,
was hilang. Oh, lost.
yeah, but that's fine if you
uh,
want to turn off the camera to probably like the camera
I want
affect
to.
the internet connection.
Oh, okay.
You can turn off the camera. But probably it's gonna be better.
Ah.
So Igede, are you still there? No? Okay.
Yeah. Technical issues. We all can
We
have.
have a technological issue. So probably you can write it down on the chat and then I can read it here. Igede. You can chat it. You can write it down there on the chat box. Okay, we go to another participants here. Alicia, are you there?
Hello, sir. I'm there.
Yes. Yeah.
Okay, sorry. I can open my camera. Okay,
No
so I
worry.
want to ask. I want to ask you about what possible operational problems could occur if steady state conditions are not achieved.
Okay.
Okay,
Yeah. So what's the problem if
that's
yeah. So the question is, so what's the problem if you cannot achieve the steady state conditions in the chemostat?
yes, sir.
Yeah.
Okay, so first, every chemostat begins with a batch process. I will say, because you need to feed, and then you need to wait until you can get what you want, and then from that you start a continuous process, so you can keep constant. There is a, a lot of problems because it depends also in the way the microorganisms are behaving and are adjusting themselves to this process. We always have a lag phase, for example, and it takes time for the microbes to start growing. But then also we start our pumps working, and we have inlet, we have outlet, and we need to, it will change at the beginning, but then you need to always be careful with the variables that you want to keep constant. So, for example, you measure the OD, you get your biomass. You measure the product in the outline, and that is good because remember that the assumption is from the outlet line, if you get a certain composition, the assumption is that that same composition is inside of the vessel. So in that way, you can manipulate the dilution rate, so you can change the parameters and help the system to reach a steady state. You might have a problems like, for example, me, when I was trying to do it and I had one leak. And one leak broke my steady state, and then I had to flush again and then start again. And these gases are like the substrate for my microbes. So if there is a leak, they start dying. So my OD start decreasing again, and you have a lot of variation in the beginning. So you can have problems like me, and it will take more time to reach the steady state because you need to keep playing with the substrates, so you can make your microbes alive again, reproduce them, and then reach again the point where you want, and keep working in that point. So you will always have probably some ups and downs until you reach the real steady state. But once you reach the steady state, well, you can have that for as long as you don't have leaks, for example, in my case.
Yeah. Yes, I actually understand. Like, it's not that easy to operate the chemostat. Yeah, you need to make it stable first. And batch fermentation actually is so important in the beginning. So in batch fermentation, you will get like some ideas, like how the profile of the cells and then the products and then the substrate. And then you also can calculate the mu max and then the specific growth rate. Then after you already determine all of the parameters, and then you can operate the chemostat. Probably it can help, like it can reduce the the time probably because you already have like some parameters there, the information of the parameters. But in reality, practically, it's so difficult to get the steady state condition. So like, yeah, as Mateo mentions, like it's so like ups and downs, ups and downs, ups and downs. So that's so difficult. All right. So how's Alicia for the answer? Is it
Okay, thank you, sir. Thank you for the answer.
no problem? And then we have another one is, I don't know, a lot of people here ask. Okay, Giza. Giza?
Yes, sir.
Yes.
Okay, is it okay if I turn off the camera?
Yeah, totally fine. No worries.
Thank you for the opportunity, sir. So I want to ask for the system of continuous flow bioreactor. I see there's an air pump and also air filter in the chemostat vessel. So what is exactly the function of the air pump and also the air filter for the process? And what is the consequences if there's a mistake from the air pump and the air filter? Thank you, sir.
No problem. So here, what is the use of the pump here, air pump and filter, and the consequence? Sorry, I actually don't get it.
No.
Did you
Yeah,
guys
it's
okay?
about the air pump
The air pump and the air filter.
so okay, I will show the graph so we can get.
Okay.
So I think it's about this.
Oh, okay. Oh, okay,
So
okay. I get it.
yeah, I mean, in this case, we can say that is an anaerobic process. So it needs probably oxygen from the air. And we always need to use a filter because that is the way of sterilize the air. So we have microbes in the air, no? And remember that if we have one small problem, we contaminate our continuous flow reactors. And getting rid of this contamination is not that easy. So we need to be careful what is getting in of the vessel. And we always use, if you are injecting air, we need the pump to push the air, and we use the filter to trap the microbes that can be there in the surroundings in the filter. So we will have air without any microbes inside of the getting into the reactor. I was having a question.
Yes. Yeah, that's so important, especially for gas fermentations and the filtration. Filtration is kind of the sterilization, because in the air, like a lot of microbes, and then we also need to filter the microbes. We need to have like the specific filter size too, just to get rid of the microorganism going into the bioreactors. And then of course we need to have that like the air pump to flow in the air into the bioreactors. So that's the answer. So how's Giza?
Okay, I get it, sir. Thank you.
Okay. Yeah, no problem. So another one, Widyarti Putri.
Thank you for the opportunity, sir.
Sure.
Let me introduce myself. My name is Widi, and I want to ask a question. So the world nowadays is increasingly focused on sustainability, recognizing the need to balance with environmental and social responsibility. So the question is, how does continuous flow bioreactor contribute to sustainable production process in the biotechnology industry? Thank you, sir.
All right, that's the interesting question. So, do you want to answer, Mateo?
Say that is one of the tools we have, no? And we decide how to use our tools. So, for example, in my case, even though the product is not helping, my product right now is a mutant strain. So directly it's not helping in any sustainable way. But if we use this mutant strain in an industrial process to upgrade biogas, then we are doing something for the environment. Also, in the continuous flow reactors, we can play with how much of this and how much of that we want to produce. So if we are producing a lot of waste because of any mean, then we will be able to play also with how much are we producing and how can we use it also in the process. Well, at least that's my idea of how can we make our process more sustainable. And we use this also continuous flow reactors. If we have a lot of biomass, a lot of product, let's say raw materials in wastes, agricultural wastes,
Yeah.
and we have a lot of tons produced every time, then we can also produce a lot of a good product and use that waste. So the good thing about these continuous flow reactors is that we can achieve high productivities.
Yeah.
So if we can achieve high productivities, then we can treat a lot of raw materials that can be contaminant at some point. So we can also use this in a sustainable ways.
Yeah. So that's good point. Yeah, I mean, especially for the chemostat, we actually in chemostat we can produce like a huge amounts of the products, and then so the raw materials that we use here is the sustainable materials. Yeah, for example, agricultural waste or agricultural materials, and the amounts of those kinds of the biomass or agricultural materials also so huge, and so yeah, I mean, like for chemostat, it's so it fits with the materials that we use here, like because it's so much, it's a huge amount. All right. So how's Vidyarthi for the answer?
I get it, sir. Thank you.
Okay. No problem. So another one is Hivan. How are you, Hivan?
I'm fine, thank you.
So go ahead.
Okay. Hello, Mr. Budi. Hello, Mr. Mateo.
Yeah.
I have a question. Mr. Mateo, you mentioned that in continuous fermentation or in chemostat, we could shorten the exponential we could shorten the exponential phase with nitrogen limitation, right? To produce penicillin much faster. From my understanding, this is different from fat batch cultivation because, for example, in microalgae cultivation, we usually promote the biomass productivity in exponential phase first, and then at the lag phase, we apply the stress such as nitrogen limitation, increasing the wavelength or the light because microalgae use light to photosynthesis. So the point is we use the stress the stress factor at the lag phase to increase the productivity of the metabolites. But why is it in the continuous phase we use the stress as at the exponential at the exponential phase? Why we shorten the exponential phase compared to fat batch?
Okay.
Okay. Yeah.
So for penicillin is not a primary metabolite. So usually primary metabolites are produced during the exponential phase because it is highly related to the main biochemical networks. For example, glycolysis or Krebs cycle. The chemicals that are produced in these cycles are called primary metabolites. But penicillin is not a primary metabolite. So it is usually produced at the end of the exponential phase and beginning of the stationary phase. So what I was saying in this chemostat is that if we are able to select that point of maximum production of penicillin that is in between the exponential phase and the stationary phase, we will have more productivity in time. So we can play, as I was saying, with the point where we want to start the chemostat. I will try to look for, would you like to say something about this? I would like to look for
Yeah, you can go
a
ahead.
graph. So
Yeah, you can.
maybe
Sure, we could look at the graph.
I think Mateo is sharing the PowerPoint here or not.
looking for a.
Have you shared the PowerPoint or not yet? Not yet.
Oh. Okay, so this is. I will try to open this picture.
Okay.
So okay, I will share now. So you seen it? Yes, you can see.
Yeah, we can see. We can see it.
So what I was saying here is that we have a lag phase here, then we have an exponential phase, and then we have a stationary phase. So this is it will be the way of starting a batch. But then you can see that penicillin is not growing along with the exponential phase. It starts growing in the end of the exponential phase and in the beginning of the stationary phase. So if you say, okay, let's start here, my continuous flow reactor, then you will have more penicillin than if you will start here, because here you have no penicillin. And then your microbes will just, if you start here, then your cells will be like this here. And they will never reach this point of among those cells where they start to produce penicillin. But if you start here and the cells keep constant in this way, you will see that penicillin will be here and even will keep like this over time. So in this way, you can increase the productivity of penicillin by selecting the point where you want to start the continuous flow reactor. That answered the question, Ivan?
So we limit the nitrogen, in the reactor when it's the end of the exponential phase. Is it correct?
Oh, usually nitrogen is like this. So we limited nitrogen because we want the cells to begin the stationary phase fast. We don't want cells, we want penicillin. So that's why.
Yeah, so probably we actually need to make like the stress conditions first for the cells to generate the penicillins. So that's why like we need to what is it like the nitrogen must be completely consumed first, and then we can start the chemostats after that. So do you think like that, Matthew?
Yeah, that's same.
Yeah. And then, yeah, especially for penicillins, that's so challenging, I think, especially for the chemostat to produce the penicillin, because penicillin is the secondary metabolite. And then this product actually is produced when the microorganisms are under the stress conditions. And then the microorganism release the penicillins here. So I think yeah, one of the strategies probably we can operate it in batch for bioreactors, but the productivity is not really good if you operate it in batch for bioreactor. But yeah, one of the strategy if you want to operate it in a chemostat is like this, I think so.
Think.
Okay,
Thank you.
so how's Ivan?
Yeah, thank you for.
Yeah, do you have any follow-up questions or it's fine?
I think it's fine.
Oh, good. Okay. Thank you for the question. So, and then also have, okay, back to Igede.
Okay, thanks for the opportunity.
Uh-huh.
Maybe I introduce myself again. My name is Igede Mukti from Pajajaran University,
Mhm.
Agroindustrial Technology, class 2023. There's something caught my eyes in adaptive laboratory evolution.
Mhm.
What triggered the microorganism to evolve? Because as I know it, the evolution is triggered by something.
Okay.
And how can we make sure the microorganism is evolving in the laboratory? Thank you.
Okay.
Okay,
I,
yeah, this is
I think that's your
interesting.
area.
Yeah.
I think we can talk a lot here.
Mm. So, what makes the microorganism to evolve? So, in nature, we have a perturbation, no? That's something that is not good for the microbe, and it just sometimes kill the microbe or sometimes reduce their growth, or it's just like a perturbation, like something that they don't like. So in nature, this used to happen. So um, I want to give like an example, but let's say, for example, the microbe cannot withstand the sunlight. So it cannot withstand the sunlight. So if you expose to sun, it will die. But then you do it again and it die again. And then you do it again. But remember that we have our genetic, like the way we reproduce is not perfect. We have mistakes. The DNA polymerase have mistakes in along when it's putting the nucleotides. Sometimes it made mistakes, and then we have another DNA, and sometimes the microbe die. But sometimes this mutation random, we don't even expect it. This will give the microbe the ability to withstand the sunlight. But this happen with a lot of time. So in nature, evolution takes millions of years. But in laboratory, that's why we introduce a lot of generations. So first thing, we don't use adaptive laboratory evolution for microbes that have a cellular cycle that is long. So if the microbes takes, for example, one neuron that takes years to reproduce, it will not be able to ALE because it will take millions of years. But if the microbe is E. coli, that you can reproduce E. coli in minutes, then you will have a lot of microbes reproducing a lot of time in every moment. Then you multiply these mutations and you multiply the opportunities to get exactly the right one you need. So evolution is a selective process. So the ones that get the advantage will survive. But disadvantage come in a random way. But then, yeah, it can be complex, but if we think about the theory of evolution, we are just decreasing the times.
Okay.
The microbe is not evolving in millions of years, it's evolving in weeks because we are reproducing and reproducing and reproducing and reproducing the microbes. So that's how you get the ability to withstand the perturbation that you want. I don't know if I was clear.
So how's Igede? So is it possible if like for example, you already make a mutant here, right? And then is it possible if the mutant go back to the wild type? So and then how to make it stable, and then you only get like the mutants, the stable mutants here.
So if you get a mutant strain, then you have another DNA. And then the idea is that it will keep this DNA as long as it's fine for it, no? So if we keep cultivating the microbe in the same conditions, with the same amount of perturbation that now is not a perturbation, we will be able to keep the same DNA, because we don't need, in this case, a lot of generations. We just need to keep this strain like this. So we will just produce a bulk and we will have it dead if we need.
Yeah, probably we need to create the same conditions, like for the same condition to the what is it, the current conditions of the microorganism, because you, for example, you already give like a lot of stress to microorganisms, and then when you want to grow the microorganisms in the bioreactor, for example, you need to use like the same conditions, right? Like the oxygen and some the certain concentration, so that's so it makes the microorganism stable there. So yeah, yeah. So how's it, Gede?
It's very clear to me, sirs. Thank you.
Yeah, it was clear, Robo.
All right, we have Nabila now.
There is also questions in the chat, Buri.
Oh yeah, we will go there after. We still have two more
Okay.
questions from, yeah. I think Nabila want to speak here. So
Okay.
yeah, Nabila.
Hello, sir. I'm
Yeah.
sorry for not being able to turn on my camera due to bad connection. My name is Nabila Putra, and I have a question about biodiesel production from ethanol, and I would like to know specifically about yeast recovery. How does recovering yeast after fermentation affect the final product of bioethanol?
Okay.
Yeah.
So when we're doing the recovery, we use a separation process to separate the microbes, the yeast, and then put it again in the fermenter. So this is used to keep a specific like concentration of biomass over time, and in this way there will be no need to introduce to reproduce, for example, again from the agar plates, enough inoculum for a big reactor, because we will have to we will just recycle the cells and put it again in the fermenter. So how it will affect? Cells are not like a machine, no? Cells are alive and they get tired, they die. So this recycle, you can use it, but not in an infinite way, because there will be a point where you will introduce the cells from the recycle system, and you will introduce cells that are not able to produce the ethanol, or produce ethanol, but in a very small concentration. And then they start also using a lot of substrate for maintenance rather than production formation. So you need to be very careful with how many times you are recycling your cells. And you need to also do experiments to know how many times you can do it.
Okay. So there is another questions, I think, about the biodiesel from ethanol. So I also wanted to confirm it. So how to produce it, like biodiesel from ethanol?
Okay. So
Yeah.
if you use ethanol and then you use, for example, palm oil, right? You need an oil, and you can use the ethanol to in the transesterification process produce
Okay.
the
Yeah, for
biodiesel.
okay, that's for applications. Yeah.
But that is, like I said, biodiesel from bioethanol,
Yeah.
but the graph
Yeah.
was just for bioethanol production.
Yeah, I understand. I thought like it was the production of biodiesel from the ethanol and through the microbial process. So you just utilize the ethanols from produced through fermentations, and then the ethanol will go to another process for biodiesel productions.
Yeah.
Yeah, that's clear. All right, so another one, Faridan. Also, Nabila. Yeah, Nabila, is it clear or you have following question?
Yeah, it's clear, sir. Thank
Okay,
you.
no problem. So we have Faridan now.
Okay. Hello, sir.
Hello, hello. Yeah,
Okay. First of all, I want to apologize because I can turn on my camera
no worries.
due
Yeah.
to the connection in here. And before I ask my question, I want to introduce myself first. My name is Faridan, and I'm from Agroindustrial Technology, Pajajaran University, class of 2023. Uh, I want to ask about parameters or what affect the process of continuous flow. Because Mr. Mateo, before this, you have previously mentioned about parameters in your response to Alessa's question. So I know it was mentioned before it, but I want to know specifically about some parameters or what can affect process of continuous flow bioreactors,
Yeah.
such as flow rate or time in specifically. Maybe
Yeah.
that's all I can ask. Thank you.
Yeah, thank you, Faridan. So that's clear questions, I think.
So the parameters,
Mhm.
I would say that the most important one would be the dilution rate because you can control your specific flow rate with this parameter. Also, the substrate's concentration, the biomass, and of course, then we have the temperature, the pH, if it's an aerobic process, then you need to keep also the transfer rate of oxygen. Or if it's a gas fermentation like me, then the right amount of gas substrate, for example, hydrogen or CO2, dissolve into the liquid and have a well-mixed environment. So, and it also depends a lot of different like configurations and what you need, no? I was saying retention time is related with dilution rate.
Yeah.
And yeah, I would say that those parameters are the ones that we need to keep an
Yeah.
eye on always.
Yes, yes. Dilution rate is so important here, right, for the chemostat. And then before I go to the chat, I'll have one more following questions like, what's the difference here between the continuous and chemostats and then fat batch fermentations? Because Hiban also mentions about the fat batch fermentations, and so what's the difference here?
So in fed batch, we have an inlet, but we have no outlet, no? So it is mainly used when a substrate concentration can be inhibitory for the microbe. So in the way we have fed batch, we can introduce substrate in lower concentrations, but over the time we can produce more and more product because we're injecting more and more substrate, but it's little by little, not a huge amount in the beginning.
Okay.
So
So do you think like fat batch is it just for several cases? It's not for general. I mean, like if someone asks you like which one is the best one, like it's batch, sorry, fat batch fermentations or continuous fermentations. What will you answer?
say that it always depends on your desired product and what you want. Because if you are using a substrate that can be inhibitory, then probably you will have to go to a fed batch. Or you can also use continuous flow reactors, but at lower concentrations of substrate.
Okay. Yeah.
Um,
Yeah, it depends on the cases. So how's Faridan? Is it clear or you still have any questions on your mind?
It's all clear, sir. Thank you.
Okay. Thank you, Faridan. So now we go to the chat. I think we have some questions here. Okay. Oh, okay. From Nurfianto Giarpangidung. Questions to Mr. Mateo. How to determine suitable substrate for microbe that will mass produce and affect in fermentation process in continuous flow bioreactor to produce specific metabolite. There are some questions here, probably one by one. The first question is how to determine a suitable substrate for microbe that will mass produce and affect in fermentation process and continuous flow bioreactor to produce specific metabolite.
So it's a good question.
Mm.
And when we have a microbe, we first need to think about from where does it come from. So usually microbes are isolated, and then we should try to replicate the environment from where they were isolated. So this is if you are doing, for example, bioprospection, you will get a microbe in some certain environmental conditions. But if you buy a strain from ATCC, that is a known cell bank, then you will have like some certain conditions and you will receive a recommendation also. You need to grow the microbe in this type of environment with these nutrients and in these conditions. So if you want to make experiments, it will be better to go back to from where it's come from. And then you will see if it's a microbe that was isolated from the sea, then you will have to inject to put more sodium, for example, inside of the solution or more salts. And it always depends on the microbe and how to do it. Batch experiments will be the easiest way to do it.
Yeah. So, and then the next question is, are you have example or experience bioreactor used for produce metabolite from bacteria for biopesticide? Do you have an experience on this research?
Pesticide.
Yeah.
Bioreactor. Well, we used to use bioreactors for producing enzymes.
Okay.
There was an enzyme that was chloroperoxidase. So you can, this enzyme can degrade colorants. So sometimes colorants are a huge problem in the water systems because they are very contaminant. And if you use chloroperoxidase, you can like degrade these colorants in a very good way. So we were trying to use bioreactors for this. It was very difficult. We got low concentration of enzyme, and we did it in a pilot plant in the university. But there was problems with agitation, with how to culture the microbe because we bought a microbe from China and it was coming to us, and we tried to replicate the microbe and it was not doing it. So we need to think a lot of things about this and how to also do the downstream process so we can get the high amount of product. It was also a challenge, but yeah, that was one of my experiences using React.
Yes. Is it possible if we can operate the chemostat especially for producing biopesticide? What do you think? That's possible?
I think it is like, for example, it's possible to produce penicillin. Biopesticides would be, I think, a secondary metabolite.
Well,
so will be possible, yes.
yeah, that's possible to produce biopesticide on a continuous flow fermentations too. So, and I want to ask again, okay, the third one, how the importance of microbe strain mutations process in produce high quality metabolite through chemostat?
Hey.
The importance of the microbe strains in produce high quality. What's the?
And
Hello?
Hello.
Oh, yeah. So,
Like, I don't understand very well.
So how the importance, how important how important the microbes is in produce high quality metabolite through chemostat. Is it important or not, the like the microbe strained, like the mutation process here, especially for to produce like a high quality of the the products? I think that's important, right? To make the microorganism mutant first.
Yeah, because usually for industrial processes, we have engineered strains
Yeah.
because these strains are capable of producing more of the product. They get inhibited in a less way, I would say. For example, yeast, you can inhibit yeast with ethanol. But if you have an engineered yeast, then you can increase that point where it became inhibit. So you will produce more ethanol over the time. So now you will not need to set the concentration at 14%. You can set it at 30%, and it will be like double the productivity.
Yeah.
So if you have a mutant strain, of course, it will increase the productivity.
Yeah. Yeah. Yeah, that's so important, especially in industry. Industry mostly they used the what is it, like the mutants, the microbes that already genetically modified by ALE or genetic engineering or metabolic engineering. So their target, the industry target is how to produce high yield and then high yield of the products. So that's why there is in industry there is the what is it, the division, or like they work on it. They work on genetic engineering or genetic modifications of the cells
to make the microbe stronger. For example,
Yeah.
my microbe, the one that I'm using, if you just open something and some air got in, you have no microbe. They die automatically.
Yeah.
So if you have an engineered strain,
Yeah.
then they will like be more strong in
Yeah.
this situation.
Yeah, that's gonna be stronger. All right. So how's Nurfianto? Is it clear or not? All of the answers are they clear? Okay, very clear. Thank you so much for the answer, Mr. Mateo. Yeah, thank you for the questions, Nurfianto. We have another one here from Ikhlas. Yeah. So may I ask a question through chat? Earlier, it was mentioned that biodiesel production can be achieved using a chemostat or other bioreactor modes. My question is it possible to scale up production using a chemostat to a level that could compete with conventional diesel production? So I think Mateo already mentioned it for the biodiesel productions here. It's not from the it's not from fermentations. The just from the ethanol that is produced from the fermentation by fermentation. So probably is it possible to scale it up? I mean, especially probably for the fermentations for for producing bioethanol here, and then after that to produce biodiesel.
Is already producing industrial scales, no?
Yeah, yeah. Is it possible
It
to
will
scale it
always,
up?
yeah, it will always depend on how much money you have, because the bigger, the more money you need to invest for sensors, for the vessel itself, for the control process, operational costs, and it depends also in how much bioethanol you want to produce, how much the market will buy. So, but they are already scaled up. Like bioethanol production is already like a huge industry.
Yeah, that's possible.
But now we need to compete with the costs, of course, because at this point it's
Oh, yeah.
cheaper to use the diesel rather than biodiesel. But I think that's what the scientific the scientific people is trying to work on right now, reducing costs so we can compete.
Yeah. Yes. Yeah, especially for the biodiesel production, we need the ethanol, and then the ethanol can be produced from the fermentations. So I think one of the solution, what the best process probably for ethanol productions now is from fermentation. Yeah. So we can use like many kinds of the sources, for example, the sugars itself, and then our biomass feedstock, lignocellulosic materials too. But even though lignocellulosic material is still challenging to produce bioethanol, but it's still possible, and then we still have the time to make it work. So I think, yeah, probably in the future we ethanol produced from the lignocellulosic materials, and it's especially for biodiesel production can compete with the conventional diesel productions later.
The idea for doing that will come from someone in this meeting and the
Yeah,
work and the research.
yeah. So, all right, very clear. Thank you, Mr. Budi and Mr. Mateo. Thank you for the questions, Ikhlas. All right, I think we still have 15 more minutes. If anyone's here want to ask again, whatever you have. So that's so interesting because our lecture is was just uh,
Like 40
less than one
minutes.
hour. Less than
Yeah.
1 hour, and then like more than 1 hour is Q&A. But I'm really glad here because you are so active. And then anything, if you have the questions, and I think that's gonna be good because here there are some experts on at the bioprocess engineering, in more specific like chemostat, and then biogas production and whatever. So if you have something on your mind and you want to ask, and just come here and then just ask. So I think we have like a lot of time to do like Q&A here and this
Mhm.
lecture. That's so interesting.
Okay.
So, if anyone want to ask again here, you anyone want to ask? No, no. I think there is no questions from
We can
the
call it a we can call
uh,
it a day. We can call it a day.
oh yeah.
Mhm.
All right. So probably we still have 12 more minutes, but there is no question. So probably if you have any questions, following up questions, then you just email Mateo, or also you also can email me. Probably email Mateo, especially for the chemostat questions. Then can you share your email here? Probably you can write it down there on the chat box.
WSU maybe?
Yeah. Can you write it down?
Yeah, I'm doing it.
Okay.
Okay.
So you can, yeah, there you go. You can save Mateo email. And if you have the questions about chemostat, about ALE process, and then you can ask Mateo. Okay. So I think that's all for today. So for the next meeting, the next lecture, my friend and Mateo's friends as well, will give a talk about bioreactor. So it's anaerobic digester in more specific. Usman will give a talk about it, and already mentions we have another lecture after the last speaker, Fuad, and then we will have another speaker. She's Anggana, and Anggana will talk about photobioreactor, especially for producing like some products from algae using the photobioreactor. That's so interesting. And then I think for the basic concepts of bioreactor engineering, it's done. Now we can go to the applications of the bioreactor. We will introduce you several bioreactor types, anaerobic digester, and then a membrane bioreactor, and then gas fermentation bioreactor. And the last one is the photobioreactor. So that's so interesting lecture. So I really hope that you can you can attend for the next lectures. Okay. So that's all. And if you don't have any questions, we can end this lecture today. And thank you so much for attending this lecture. And wassalamualaikum warahmatullahi wabarakatuh.